Okay, for FIT, you have Catharina Stroppel from University of Bonn, so you can start our first
Okay, thanks very much for the invitation. So somehow this talk, I thought I give a little bit of overview talk with old stuff, which is known, and then next talk will be new stuff. So maybe some of you are bored. So tell me when you are bored, then I skip things. And you can always, of course, interrupt me and say I should explain stuff. But I just thought I say a little bit how maybe the point of views might be different so that we can talk in the next few days. So let me start with number one. We want to understand link and tangle invariants. So this is talk today. That's number one. Number two, we want maybe to talk about TQFTs. So what I have in mind for link and tangle invariants are, for instance, the Jones polynomial and the ratio Tk/half invariants. So today everything will be only type A. It's already evolving for everybody. And for number two, TQFTs, I have in mind, of course, for you guys, it's maybe Chern-Simons theory. And for me, it's more ratio Tk/half width and three manifold invariants. So, and these two things are for me maybe more different worlds than for you. For me, number one is coming from a quantum group for generic Q. And number two is coming from a quantum group for root of unity. And I think at the moment, we have no idea how to categorify really root of unity. There are some approaches, but nothing is satisfactory. And so it's really some sort of different worlds. And what I also want to emphasize, right, there is many approaches to what we want to understand of link invariants. So we want to compute a Jones polynomial. But actually, I want to understand a bit more because everything comes from a braided monoidal category. So in these examples, it's the category of representations for quantum UQG modules. So I really want to understand the whole category. So if you just give me the Jones polynomial and I want to categorify the Jones polynomial, then I'm unhappy. So that's the whole thing. And this will also be then relevant for the second talk to get towards some TQFT. So now we want to do categorification, and to do this, I want to start with the Jones polynomial and just say some basic things to hopefully come to the, to have the same language. So for me, there is different approaches to categorification of the Jones polynomial. So the first one is, so I explained it first, decategorified, is starting from the Kaufman bracket. So you take a knot, drawn here. I have a crossing. The philosophy is we don't like crossings. We resolve crossings by cap minus the identity, and then there's a quantum Q inverse or whatever, how you normalize it, and then an overall factor afterwards to get an invariant. So important for me is that this is a very nice construction. It's easy to compute. One drawback is it only works for links. Okay. So second thing is I realize a knot as a braid closure. And that's already something I have to put in. It has to come as a braid closure. Then one might read this picture as the following. I cut it into three pieces. At the bottom, I have a vector. In the middle, I have a matrix, which is, I call it a braiding matrix. At the top, I have a vector. And then I apply this matrix to the vector, and I pair it with the vector, and I get a polynomial itself. Okay, this, again, it only works for certain things. It only works for braid closures. Good. So now next thing is the full ratio Tk/half theory. So this is the idea. I take quantum as a two representation. So here V is the natural representation for the Jones polynomial. I take tensor products of this, threefold tensor product, fivefold tensor product, and then a tangle is for me a morphism going from this threefold to this fivefold tensor product. Or in other words, an intertwiner, so a morphism of UQ as a two representations. Okay? So, and the advantage of this is it works for arbitrary tangles. And it also, by construction, sees the braided monoidal category. So, and whatever I want to do concerning categorification, I would like to see as much as possible of the underlying binding monoidal category. And somehow here and here, this is somehow by construction not visible. Yeah? Everybody happy? Okay, so now let's, maybe I should explain the other two things which are on this slide. So there is also the way that we can take a link as a braid closure and then use traces to construct a Humphrey PT polynomial, which is a polynomial which has two parameters, Q inverse and A. And so we can specialize A to Q squared to get the Jones polynomial. So this is something I don't want to talk about today, because it's from a categorified point of view, it's, for me at least, a slightly different word. And so I want to ignore it. And maybe say something at the end, how it fits in. And I just want to say somehow this Reshetik into Howe for me is the thing which sees all the other sides. So I can go from here to here, of course, by looking at 0, 0 tangles. So the 0-fold tensor product to the 0-fold tensor product going here. And also somehow this smoothing can be seen in here, just by expressing the crossing in terms of other generators. And then going from there to there just means I plug in certain vectors. So a linear map is defined by saying what it does on every basis vector. And in this sort of point of view, I only pick specific closures. So here's one specific choice, this sort of nested cups. I could also close it another way. So I pick one specific basis vector and I evaluated that one. So going from here to here loses some kind of information. But to have just the invariant, it's enough. But I'm not happy if I want to keep the whole tensor category. Okay. So now what about categorification? I mean, this sort of picture, I would say, is the original categorification of Havanov with his cube of resolutions. He did exactly this. So he took his knots, then he resolved it. And for every of these guys, he put it down a vector space for every circle, a two-dimensional vector space, and he constructed a cube of resolutions. So it's mumbo jumbo that it works exactly in this roughly same way as if you know nothing and just the Kaufman bracket. I think it's surprising that it actually works. So here on this side, this is for me, for instance, Seidel-Smith theory. So what do? They take what is upstairs a vector, L is a Lagrangian, V is a Lagrangian L. The braid matrix is some kind of twist. The other vector is another Lagrangian, and then the pairing is the Floer homology. So, and this is maybe your world, I don't know where you are at home, roughly.
I'm not heading to the, one has to modify the theory.
They don't have Q. Okay, then maybe I should say Seidel-Smith plus the new version Abu Zaid Smith, where they introduced somehow a two-parameter version and have everything. And then they are also very close to this, but not there yet. And so, and this side, this is, I think, where Lie theory is giving a good answer, and where all these algebraic categorifications using KLR algebras and related things are at home. Okay. And I don't know, maybe I missed many things, just a rough idea. So now, just to put everything together, I want to combine now everything. So what I want to have is I want to have the tensor product of the quantum SL2. In between, we have this intertwiners, which give us the tangles. I want to see the quantum group action. I also want to keep track of the Kaufman idea. I want to be able to resolve these crossings by some smoothing. I get these pictures. So I forgot the Qs. But these pictures are for me from a slightly different world. They are coming from a temporally lead algebra. So if I have crossing-less matchings, tangles without crossings, these can be composed in the obvious way. And this is exactly what people call, after linearization over Q, it's a temporally lead algebra. Okay, so these are the ingredients, and I want to have a categorification where you can see at least these ones, and hopefully everything which representation theories want to know. And so most of the theories take one piece of it and are happy with it, because it's enough for not invariants, but we would like to put them together. So, and also, often in the literature, one decides, one has either the quantum as a two action, and one said, okay, we would like to categorify quantum groups. There's many examples of this. For instance, Rucke, Pavan of Lauda, two Kac-Moody representations, or one looks at intertwiners. That means the link invariants. But we want to have a picture where both of them are visible. And so, so Webster did it partially. Okay. So I think Lie theoretic and the resulting algebraic categorification, this includes Webster, but I think in type A. So I don't think outside type A he has really those pictures. And the reason is the following. So in general, when you do diagrammatic categorifications, you draw things in terms of diagrams. So what you can do reasonably well, you can write down bimodules and functors which come from bimodules, tensoring with bimodules. But as soon as you have to derive them, it's pretty complicated because diagrammatics is not built to describe derived functors. Theory, abstract theory, is good for doing things with derived functors. So I think Ben's work works in type A, and outside type A, first of all, it has a problem with its diagrammatics, and you can't write down derived functors. And whatever you do, if you decide on one side to be the nice side, it will be nice exact functors, which are the building blocks. The other side will be from the beginning derived. And so I think it's hopeless to hope that you have a picture which combines all sides, which is diagrammatic. So that's my belief. So yeah. And the other thing is when you are outside type A, there's also a big problem that somehow the things which are easy for us to describe, also in Webster's world, which are related to Hecke algebras, etc., is not the centralizer of the quantum group. They are often centralizers of each other. So that means what is often missing in the theory outside type A is that the left-hand side, the intertwiners, is really the centralizer of the quantum group action, and not less and not more. And so yeah, so this is. But I definitely put Webster in this world where things are nice, very nice. And they don't have, so they have one side, they do one side, and then they write another paper where they do the other side, but they can't put them together. And it's intrinsic that they can't put them together.
The orientations of some arrows and the job for them.
So the thing is, I will come to this later. The thing is, you can, whenever you decide which side you do, you can do it with the same language. And I will explain afterwards later why this is the case. But if you decide one side to be done in diagrammatics, you have to pay a price, and the other side doesn't work. You can go home and say next day, oh, I want to do the other side. I start from the other side, but then the first side doesn't work. That's, yeah. Do you disagree? We agree. So now there's another thing which I briefly want to comment on. There's some specific thing about categorifying SLK invariants. So for SLK and k equals to 2, we have some nice coincidence. Namely, the natural representation is isomorphic to its dual, and it's isomorphic to the k minus first exterior power of the natural representation. That's very specific. And why is this a nice thing? This is a nice thing because so when you start with your link, you draw your link, like this, whatever, then the orientation would tell you in the web station theory of Reshetkin and Touraev that you work with V or V dual. This would be the right picture. But if V is isomorphic to V dual, I can ignore this, remove it, remove the orientation, do the Kaufman bracket calculation, and afterwards I just renormalize to put in the orientation back. So this is why Howanov homology works. He really forgets the orientation, does some calculation, and at the end he renormalizes. So, but I mean, what is obvious to expect is if I do something which is not natural, I just do it by accident, it's not factorial. So Howanov homology is not factorial, it's only factorial up to signs. So if you take Howanov homology, which gives invariance of tangles or links, and you want to extend it to cobordisms, it's known that it doesn't work. And so there were several fixes by several people. And so to explain this fix, I want to say another thing which is special for SL, for any SLK, it's that the trivial web station is isomorphic to the exterior power of the natural web station. Yeah, because if you think in terms of the group instead of the Lie algebra, the determinant of the group is 1 if I take SL. So it's the same thing. So which means, so the thing which Reshetkin Touraev tells us to do is I take, for instance, for this cup, I take V dual tensor V, and I take a map to the trivial web station. So now, instead, I could write here the K minus first exterior power of V, tensor V, and I can go to the full exterior power. Okay? And so the thing is, this is actually better. and this kind of world, I can also do for GLK. And in GLK, this is not true anymore. It makes a difference. So this makes sense for GK, and you can define all the other ones as well. I mean, you just swap the two tensor factors, you do have the same obvious map. And the map in the opposite direction is just taking this wedge product and separate it in all possible ways and sum it up with some Q powers. Okay.
So say it makes sense for GLK when you write down this cap. Do you need to add some dashed line to represent the much K going out?
Here?
Yeah.
So when you do then this, I agree, you should really write that thing. Exactly. But of course, topologists would never write this, but you should, because yeah. Okay. And so the point is that there is the GL2 version of Howanov homology where you just do this sort of thing. And it's the same thing as for normal Howanov homology, but you have some signs involved. And so we wrote this up. You still get invariance of links and you get the same invariance. So the invariants don't change. It's natural. And so we wrote this up, but it's based on previous work which inspired us. Several people tried to fix this. And then it was also afterwards generalized to arbitrary K. We did it for K equals to 2 by Tubenhauer, Wedrich, and Wilbert. And what is behind this is then signed arc algebras instead of arc algebras. And so the computations are awful, I have to say. I don't recommend to work with it in practice, but it becomes functorial. So, and it's an extension of Blanchet's invariance of knots and tangles. So he constructed what I would call forms with singular seams. So I just give the principal idea. So when I take this crossing, for instance, and I resolve it in the Kaufman bracket way, so I ignore all the Q powers. So you see already that this is pretty bad. Somehow it cannot work. And the reason why it cannot work, because this is oriented upwards. If I put it here, I get in trouble. I can put it here, but I can't put it here. And whatever you do with the orientation here, one of them will work and the other one will not work. So this indicates already that there is some problem with this smoothing. But if you think in GLK version, then your crossing would be resolved like this. So this in the middle is this dashed line over there. And then you'd go together, you merge them and split them. And here you have the identity, and you can put orientations on top. And you see it's a better theory. Okay, so that means this hopefully shows that we should work with GLK and not with SLK.
Here you restate B tends to B star, which actually does go to a trivial representation. There is not one in this picture on the board.
In this one, no, so there's this picture. So this goes from V tensor V star to the trivial. But this picture, this goes from V tensor wedge K minus 1V to wedge KV. And this is what I want to do. And for SLK, it doesn't make a difference. But for GL, it makes a difference. And I really want to categorify this stuff. And the claim is, and I mean, several people worked on this and tried to convince people, is when you do this categorification correctly, then Howano homology becomes functorial. And so for people who know circle bimodules, that's also the idea behind circle bimodules, where similar pictures appear. Okay. So if you believe this now, what we have to understand is the braided monoidal category of tensor products of exterior powers of V. And this is the thing which we should categorify with all the structure which we have. Braided monoidal and whatever. So I introduced some notation. So V is the natural representation for GLK now. And I want to take tensor products of exterior powers, and I just denote them by wedge A underlined V. Yeah. Oh, I wrote here SLK, but actually I want to have GLK. But yeah, if you prefer SLK, it's fine. So then there's a fact, and the fact is that intertwiners between such modules are generated by this basic things. So it's exactly what we have. We can go from wedge A tensor wedge B to wedge A plus B just by wedging together. And we can also go the opposite way by putting it apart in all possible ways. And of course, I have to do this in a quantum version, so I don't want to write down the formulas, but I guess you can, first of all, imagine them, and secondly, you would be much faster writing it. Okay. So there's in fact a universal web category. So a web category, that's a monoidal category where objects are natural numbers, including zeros. This is the A and B and the B's. And the morphisms are the generators. The generators of the morphisms are these things. This merge.
Why? So you could try to write down a general theory of graphs, which would have more stuff. There'd be more trivial inversions. But you say this is it's enough to generate everything for us.
What would be an example for more trivial inversions?
Well, just in the tensor product of two antisymmetric representations. There's the maximal and antisymmetric, but there are also a whole bunch of other stuff. So it's not these diagrams don't describe just huge products.
So I only take tensor products of exterior powers. That's the first thing, maybe, which you. So why?
No, I know that you can do it. That this is the demo why.
So yeah, so that means you take these mergings and the splits, and you generate monoidally, which means you put them next to each other and you put them on top of each other with identities, and this is all you can build. Yeah. So, and then there are the relations. So here the associativity and the coassociativity relation. And then there's this relation here. So, first of all,
what do you say? This is some magic of SLN, right? Which will not, or GLN, it will not work.
I mean,
magic may not exist. There's no principle that defines magic. It's a magic.
There is a principle behind this. There's a principle, and I might say Maybe I say something later about it. So in general, there's people like Kuperberg who try to find these webs and for every Lie algebras. And so there are some kind of answers. The explanation where they come from, there is a very nice explanation for type A. I will explain later. And then I can also say why it's harder in other cases. So what I want to say first is that it's enough actually to look at such guys where I have A plus 1, A and 1. So in principle, what you do, you merge A and B together to A plus B. But because of this associativity and co-associativity, I can merge not A, B all together to A plus B in one step. But I could take out of B the first one guy out, and then the second guy out, third guy out, etc., and go to here. So if I have these kind of generators and upside down ones, I can create them. And vice versa, of course, if I have them, I also have these. So, and then here is a relation which says, if I have A and I split off 1, and I put it together with the B, wait, I should look at here. So I take the A, I split it off, I take the 1 to the B, and I put it back to the A. Yeah, and on that side, I start from the B, I move one step to the A, and then I move it back to B. So if I call moving to the right an F, moving to a left an E, then I would have a formula like this. Yeah. So this is like a quantum group relation for SL2. On the other side, I have identity and then a coefficient. So let's ignore this eta. I have A minus B. So this is just some number n times the identity.
Just make sure your ABs are like from 1 to K, or it can be arbitrary numbers.
So AB, they are from, so in this world, they are from N0. But of course, you want to have that wedge K of C to the K, wedge M of C to the K 0 for M bigger than K, right? So here I have the universal web category. So universal refers to that I take all GLKs together. So I don't want to have a condition like this. But then if I take this universal one, and then I want to go to the specific UQ GLK, you ask the question, which relation do I have to put? And then what Kautis and Chemnitz and Marsden actually proved, they gave generated relation, they proved it's enough to exactly kill all the strands, all the labels, which are bigger than K. So that means in the quotient describing UQ GLK, you actually only allow the correct labels. Okay, so now what do I want to explain here? Here I want to explain that this relation looks like a relation of this form. And if I think of a SL2 module, and I have a specific weight space, then EF minus FE acts like K minus K inverse divided by Q minus Q inverse. And let's say the weight space is n, it's weight n, then this is Q to the n minus Q to the minus n divided by Q minus Q inverse. And this is exactly quantum. Yeah. So that means this relation is really something which indicates it has to do with some Lie algebra. But the confusing thing is, these are supposed to be the intertwiners. So there shouldn't be a Lie algebra coming up. And so the question is, why does this strange relation hold here? We wouldn't expect a Lie algebra. Yep. Okay. So and I mean, how should you think in terms of these webs in connection to what I said before? So I started with this Kaufman bracket, which was categorified by Hovanov, where we smoothen all the crossings. You should think of when I take an arbitrary tangle for UQ, SLK, or GLK, and you smoothen it, what you get is these webs. The webs is the analog of the temporal leap stuff I had before.
Not smoothing, but flattening. But they are not smooth.
Okay. Smoothen the crossings. Smoothen the crossings and don't do whatever. Yeah. Okay, so now what I want to explain now, why the hell these guys come up, this quantum group relations. And I mean, the answer, I guess many of you know already, but I want to nevertheless explain it. And I want to play a game with you guys. Yeah?
That read out the relation, not by like the strings, but by pair of times, what we get.
You want to make this in terms of pairs of pens?
Yeah.
Yes. So this is exactly when you take a two-dimensional TQFT and you take pair of pens, then this would be the associativity and this is the co-associativity, but you don't have this relation. So it looks very similar. I think it's up to the point that if you describe two-dimensional TQFTs in terms of cobordisms, many people flatten it and do calculations with such web diagrams, but they have slightly different relations because they replace this sort of interesting relation, which I want to explain, with the Frobenius relation. So it looks similar, but I think it's not directly connected. Yeah.
I'm also wondering that if the first two diagrams that represent something such as in TQFT, you have when you do anomaly in flow S, the relations imply that there is a two consecutive conditions for the projection representation.
I'm not sure if I understood the question. Can you say it again?
The TQFT and there are anomalies.
Yes.
You can fusion the anomaly into new one.
Yes.
And that condition implies that the coefficient of the projected representation of
yes.
There are some critical cycle conditions, right? Something related to quality. Are there similar things?
Yes, I think it's similar, but I think behind this there is some kind of similar picture because you do fusion. This is what you do. But altogether, the relation comes really from a simpler thing, namely when you take wedge products, it's just associative. It's the only thing which says when I wedge A and B together and afterwards C, it's the same thing as wedging first B and C and then afterwards A with it. So I think it's much easier, but behind it is of course a fusion construction. So maybe I also should say something about this funny eta here. So in the Jones polynomial, when you look at the literature, there's different normalization. Sometimes the unknot is Q plus Q inverse, and sometimes it's minus Q inverse. So I put this here, I sneak it in with minus eta, and eta is plus minus 1. So there's in principle two different words. You put the sign or you don't put the sign. And for me, they are Cauchy dual, and it has really a meaning whether I put it or not put it. For most people, it's just a question of normalization. But for me, the one normalization is Cauchy dual to the other normalization. So we, in principle, would like to have both parameterizations. So, okay, but now let's play a combinatorial game. So a very easy combinatorial game. What are the possibilities to put 4 balls into 3 times 2, which is 6 boxes? And I realized this morning that I threw the boxes opposite to how one would draw matrices. So, but okay, it's a Russian style to draw a matrix. So, of course, we have 6 choose 4 possibilities, which is 15. So I drew them here. Everybody happy? Does everybody agree? No, sorry. I should say this. You put only one ball into a box. At most 1 ball. Okay, so we have this. So now how do we encode the possibilities? I want to encode the possibilities as I take 3 times 2, so a 3-dimensional space and a 2-dimensional space. Tensor them together. This is a 6-dimensional space, and I take wedge 4 of it. Do you agree that this is the same basis vectors? Just count basis vectors, the same number.
Always supposed to be representations or nothing.
So at the moment they are vector spaces, but of course I'm a representation series, so they are supposed to be representations. But at the moment they are not yet. Yeah, but I think of it as a the standard representation of GL3 and the standard representation of GL2. Okay. So, and I want to think of first column, first standard basis, second column standard, second basis, third column, third standard basis of V3, for instance. So, it's hard to distinguish the colors now. So what I mark now with colors is the first 2 pictures have 3 balls in the top row, right? The blue pictures have 2 balls in the top and 2 balls in the bottom, and the last picture has 3 balls in the bottom. So I claim distinguishing in these 3 colors means I want to say the first thing is something like wedge 3 of V, tensor wedge 1 of V. But it's wedge 3 of V3 and wedge 1 of V3. Second is wedge 2, tensor wedge 2, and the last one is wedge 1, tensor wedge 3. Yeah? So I just count somehow numbers. So, but I could also do it in the opposite way. So now I marked in yellow the ones which have 2 balls in the first column, 1 in the second, 1 in the third. Okay, there's 4 possibilities. Then in green I have 1, 2, 1, and then whatever. Here, for instance, I have 0, 2, 2. Okay, so I can read it in these 3 ways. Yeah, and so the last way would give me here, for instance, in yellow, something which is in wedge 2 of V2, tensor wedge 1 of V2, tensor wedge 1 of V2. Yeah, and so 3 ways to count the same thing. And so
how many concrete colors do you have here?
How many colors?
Concrete colors.
So I have the yellow, which is 2, 1, 1. I have the green, which is 1, 2, 1. I have the blue, which is 1, 1, 2. And then I have the pink, which is 2, 2, 0. And I have the brown, which is 2, 0, 2. And I have the 1, 0, 2, 2. Yeah. Okay. So, and behind this very stupid counting, there is skew Howe duality. What does skew Howe duality mean? So we started with our wedge 4 of V3 tensor wedge V2. This is a representation. Now the representation comes in of GL2 box GL3 box GL2. So box means I really act totally independently on V3 with GL3 and on V2 with GL2. Obviously they commute. Yeah. And now take your basis vectors in here, put them into these box diagrams. Now we had 2 other ways to read the box diagrams, either along the rows or along the columns. And so this means that I have an isomorphism, either as a GL3 module or as a GL2 module, depending on which way of reading I do, to the following things. So in one version, I had always V3 as the representation, but I sum over all possibilities to put the boxes in the first row or in the second row. And in the second guy, I had V2s, and I have all the possibilities in the first, second, or third column. And so I claim there's an isomorphism of vector spaces. And this isomorphism of vector spaces is compatible with the GL3 action in the first case and with the GL2 action in the second case. And so this means, in particular, when I start with the top thing, this GL3 representation, and I go through the isomorphism, it inherits a GL2 action in a not totally obvious way. And vice versa, the bottom thing inherits a representation of GL3. So in terms of box diagrams, I have two Lie algebra actions. So one acts by moving balls along rows, and the other one acts by moving balls along columns. And they just act how they act on the natural representation. And obviously, it doesn't matter what you do first, moving like this or moving like, and then like this or vice versa. So commuting actions. But this also says, because at the beginning, the commutator is just the other Lie algebra, on this direct sum of exterior powers, the commutator is coming from another Lie algebra. And so this explains us why there's some kind of Lie algebra relation in this web calculus. Yeah? And so, yeah, intertwiners are determined by a Lie algebra. So that means if I want to categorify, I can forget about all these tangles and whatever. I just have to categorify Lie algebra actions. And then everything else is supposed to just come automatically. Yeah? Because intertwiners between such representations are given by another GL action. It's maybe not an obvious one, but it is there. And another thing which one might observe is when I look back at this combinatorics here, so the one thing was looking at how many balls are in the first and in the second row. So this was the exterior powers. And the second thing was looking at how many are in the columns. And the columns tell me how many first basis vectors do I have, how many second basis vectors do I have, how many third basis vectors I have. So they encode for me the weights. So that means what I really have is modules for the one side are weight spaces for the other side. When should I actually stop? I have 2 hours. Okay, I have 2 hours. Good. So, so that means more formally, this skew-Howe duality is doing the following thing. So I have a sum of exterior powers. We encode somehow the exponents. So in our case, the exponents went between 0 and 3, for instance. And at the other side, I have the weight spaces in blue downstairs. And the fixed n, this was our total number. This was 4 in this case. So n was the number of balls. But reading it in the opposite way, the two things swap. I have the exterior power becomes now the B. So the blue B becomes the green B, and the green A becomes the blue A. So they swap. So this is what I call skew-Howe duality, or what people call skew-Howe duality. So this was proven by Howe. And now we want to categorify this. So if we categorify this, then I claim, so the Lie theoretic world is the following. So I first give a rough picture, and then I say a little bit more on the board. So there is a category which depends on n. So this is the total number of balls. Then I have 2 parameters, A and B. One I call the parabolic condition, the other one I call a centralizer condition. I take some derived category of this. And then this is a category which is Cauchy self-dual, but the whole, so I forgot the sum. There should be a sum outside, sum over A and B. The whole sum is Cauchy self-dual, but each summand is not self-dual. if I take the dual of the summand, I get the flip vector. So the role of A becomes thing here. So parabolic and central get swapped. This central gets this parabolic.
In explicit terms, the A and T, A bar represent what number of boxes and rows?
So in the picture with the boxes, yeah, let's go back again.
Like each term corresponds to a term, a choice of A and B.
Yes. So here in this picture, for instance, the first picture has 3 guys at the top. This is this exterior 3, and 1 guy in the bottom. It is exterior 1. So it lives in this exterior product, but then it has a certain weight. Yeah. So if you think of this V as the natural representation, then this weight vector, so this is V1, wedge V2, wedge V3. So because it's first box, second box, third box, tensor V1. So that means the weight is 2 times V1, 1 times V2, and 1 times V3, the weight of this thing. And so that means what is it? The columns encode the weight and the rows encode the exterior power. But if I read it in the opposite, way like this, then the 2 things get swapped. The same picture has 2 meanings. Exactly. Yeah, exactly. And so
after you take the direct sum of A and B?
yes, I forgot here that I have to take the direct sum. So no, this is actually true in general for fixed A and B. But what I want is to have this.
You want to
Exactly on the same thing. So this is true for fixed A and B, but if I take the direct sum of say D categorified of this thing over A and B, this is the thing which has 2 actions. Yeah? So and having this, I can construct functors realizing one of the Lie algebra actions on one side, and I do it in my favorite theory, whatever you want to do. And then you go via partial duality to the other side, and you get the corresponding other side on this guy. And when you identify the 2 things, you get both functors. So this allows you just to pick the nice one. Okay? So should I quickly say what these categories are? So we have N, capital N. This was before 4. This is the total number of balls. And now I introduce another GL, but this GL unfortunately has absolutely nothing to do with the quantum whatever we had before. Yeah? So we take GLN, and then what we do is this category O. So this is modules, representations for GLN, which have a weight space decomposition, and on which the Borel, the upper triangular matrices, act locally nilpotently. Okay? So now I make this stronger. So inside there, I have 2 things. I have a dependence on a parabolic P. So P, I can also call PA. So this is just a standard parabolic. Looks like this. I have A1, A2, up to AR here. These are the sizes of the blocks. And by definition, they sum up to N. In the same way as in our box thing, the number of balls in each row separately sum up to the total number of balls, which is N. Okay? And so this thing is a subcategory in here, where I say I take only web stations which are locally finite with respect to this parabolic. So every vector is contained in a finite dimensional web station for this PA. So in the full extreme case where I take P to be the full Lie algebra G, so I have only one A and this is N, I get finite dimensional web stations. And the other extreme, when everything is 1, 1, 1, I get the normal category O. So it goes between finite dimensionals and the normal category O. So in particular, these categories, this has Verma modules and this has parabolic Verma modules. And in this categorification, the box diagrams correspond to the Verma modules. So and I can also do something else. So if I have a web station here, I can ask the question, what is its central character? And a central character is given by, so I usually draw some hyperplanes, and then you look at the singularity of the central character. It can be a regular character lying inside a chamber, and it doesn't matter where, or it lies on a wall, or it lies here. So you can look at the stabilizer of the centralizer, because that's the only thing which matters. So the stabilizer is a subgroup of the Y group, W, and it's of the form SB1 times SB2 times SBL. So where these are symmetric groups inside the full symmetric group. So that again, B1, B2 up to the sum of the BIs has to be equal to N, because this is S. Okay. So, and I can put this here. So I fix this B, and I just put a B here. Okay. So I have these two versions, and then I can combine them. I can take the intersection. So and if you prefer geometry, you can say, okay, this category O is equivalent to pivot sheaves on flat whiteys. This category O is equivalent to pivot sheaves on partial flat whiteys. But then putting this condition in is something highly non-trivial. So then this sort of thing, one might think in terms of a Cauchy dual picture in terms of D modules, but then putting this condition is also non-trivial. So geometrically combining the two is a bit annoying. Algebraically, it's not difficult. Huh? And then this equivalence of categories, it just goes take a Verma module here, encode its highest weight. So there's a very easy way to translate it into such a box diagram. Read the box diagram in the opposite direction, encode it again as a weight. You get a Verma module here. And this Cauchy duality sends this Verma for the box diagram read in one way to the Verma for the box diagram read in the other way. So it's pretty simple. Yeah. And then if you have these Verma modules, then the action of the quantum group is just moving your boxes along walls or along.
So we have a subscript P to produce this subgroup of the value, and you require no weights set by the activity.
Exactly. Invariant under this subgroup. And usually I mean, of course, you have many possibilities to choose them with this same stabilizer. But you make a specific choice, which comes from really encoding. So I go back here again. So if I write such a thing in here, V1, V2, V3, tensor V1, I more or less just take the indices. I have 1, 1, 2, 1, 2, and 1, 3, and I put them somehow as coefficients of as weights. So I have a weight which is 1, 2, 3, 1. And then I have automatically the correct stabilizer.
In this picture, GO2 and GO3 are important. I mean, on this
Yeah.
slide. And on the next slide, what's the analog of that?
On the
Like,
next
more general side, what replaces GO2 and GO3? Here, not in the next one.
Next one. Here.
Yeah.
Ah, so no, they are not lost. So I fixed the n.
Oh, the N. Yeah.
It's the GLM and the GLN. Yeah. So I take here parabolics which have these block sizes. They add up to n, but I fix the number of blocks. And the number of blocks, maybe I should call this now m to make it consistent. The number of blocks is somehow the Lie algebra GLM on the other side. Yeah, exactly.
So this is somehow complicated mirror symmetry, but in 3D mirror symmetry, there.
So the class code that we are talking about here.
But
And so one thing which I should maybe also say. So if one takes V tensor n, we say SL2.
yeah, no, I think about it.
If I do this is sitting inside this picture because this is wedge 1 of V tensor, wedge 1 of V tensor, blah blah blah. But it's sitting only as a piece. So it's one of the summons in the big picture. So it's a module for this, but it's a weight space for the other side. So that means here you don't have the action of GLN because it's only a weight space. So you only have the whatever Hecke algebra or symmetric group acting. But this is because you do a too small picture. So that means here you don't have this very nice duality because you make it too small. But adding all this stuff up here upstairs, this gives you a space where really there is enough room to have a symmetric picture. And so sure, Weil duality one should somehow forget because it's not symmetric. But this Q-Howe duality is symmetric. And maybe now related to other Lie algebra things. So there is Howe dualities or skew Howe dualities for other Lie algebras, like SO and SP. So then there is somehow dual versions. Langland's dual, I mean the one side is Langland's dual to the other. But this only works for non-quantized. So what I described to you here, it works for quantized. If you do not type A, you can't do it quantized. Except when you replace, on the one hand side, there's the quantum group SO, and on the other side, you have to replace it by some other quantization, which is not a Hopf algebra. It's a co-ideal subalgebra. And you can do this in both ways. So either SO and co-ideal SP or SP and co-ideal SO. And so co-ideal is, so you have you have a Lie algebra G, and you have a subalgebra G given by fixed points under an involution, like SO. Then you have the universal enveloping algebra and sits inside universal enveloping algebra here. So this works. This is a Hopf subalgebra in here. So that means tensor products and so on makes sense. Now you want to do this. And then this still embeds as subalgebra, but not as Hopf subalgebra. So, but you can define a quantization here slightly differently. I put a primed. So it has the same Q equals to 1 limit. But it has only the property when I take the co-multiplication of something in here. So let me call this U prime. Then it ends up in U prime tensor U. And so it's a prime tier, but it's not a prime tier. So that means if I just take tensor products of representations for the small thing, it doesn't work. You cannot act on it. You can only act on things, tensor product of something from the small and something from the big. And so for me, this world is much more difficult than type A. So that's one of the reasons why I think we haven't understood this completely yet. Despite of Ben's stuff, there's lots of things which still have to be done. Okay. So now I want to say something about the action of the Lie algebras. So now we have these categories, and now I want to. So I said one of them encodes a weight space, and the other one encodes a representation. So let's say the P's encode the weight space at the moment. So when I act with the quantum group, I want to go from one weight space to the other. So in this case, I want to go, for instance, in the easiest situation from this parabolic corresponding to A1, A2 to the parabolic where I increase one of them and decrease the other one. This is the neighbored one. And I can go to this via correspondence because over these two parabolics, there's the smallest parabolic sitting over with A1 minus 1, 1, and A2 minus 1. So in correspondence, it just means I can take a module in here, in the left-hand side. So this is a module which is locally finite for the parabolic upstairs on the left. Then I can project onto the quotient of all representations which are locally finite for the big parabolic on the top. And then I can include it into the other one. Yeah, and so this gives me nice correspondence. And you just check what it does on Weber modules. And it does the right thing, and it gives the correct comment. So, and then on the other side, what can I do with this value here? I can take a module, GLM module with a central character B. I can tensor with any finite dimension module, in particular with the natural representation. I get something which has many summands maybe, but I can pick out the summand which has the correct centralizer where I want to go to, B prime. And so this gives also functors. And when I tensor with a finite dimensional module, it somehow preserves all the finiteness conditions I have for parabolics. So these two things naturally commute. And so these are the two sides of functors which act on the same kind of categories, and they by construction commute. And so I prefer the translation functors because they are really like exact functors on the nose. The other ones you have to derive honestly. So that's the sort of thing one would prefer. And this is also what Hovanov's theory is built on. And so under this Koszul duality, the Q grading goes to minus Q or minus Q inverse grading. And so this is exactly these different normalizations in the Jones polynomial, either quantum 2 or minus quantum 2 for the unknot. So the fact that Hovanov has quantum 2 in his normalization means actually he works in this picture and not with the other picture. Yeah. Yeah, exactly. So, and now just to summarize, when I combine everything from the beginning.
So in the Ferrari equivalent categories, people understand the Koszul grading? How
yeah, you understand everything. Everything, yeah. Yeah.
When you insist on both parabolic and central character condition, can I think of this as like module zero quantization, but it's slides inside the norm term to GLN?
Ah, yes. So you can so roughly, the parabolic condition means I work with partial flag varieties, G mod P.
Yeah.
And then you can put a Springer condition, X, where you say, I only take the partial flags which are fixed under nilpotent or unipotent. And so this condition is exactly like a Slaughter-Wissler condition. So you can embed this into a compactified, for me, always a compactified resolution of a Slaughter-Wissler. And then you can see these sort of parabolic categories in terms of quantizations of this. But I don't think anybody actually worked out precisely what the mix of these two things is. As far as I know, it's only one picture is done. I mean, either this or this. Yeah. Yeah. So and so at the end, I just want to summarize that we can see the things which I wanted to see before. So we have this category, and you can cut to whatever you want, this tensor product of these V's, for instance. Then you have two kind of functors. One are these parabolic correspondences, and then these translation functors or complexes of translation functors. And it's a complexes because when I would smoothen it, I get this sort of these pictures without crossings, and they correspond really to these exact translation functors. And the pictures mean just I go from some central character to another central character. Either I merge or I split. Yeah. And so at the end, everything is really reduced to categorified Lie algebra actions. And for categorified Lie algebra actions, there is nowadays a definition what this means. There is this U dot two category, Kac-Moody two category. So an action means we want to have an action of this thing. So and the statement is this is a proper two Kac-Moody categorification for both sides. But for one side, for this one, we have really exact functors, which we want to have from this theory. So from this side, it's somehow on the nose. This side is unfortunately derived. But because of Cauchy duality, we have a distinguished non-standard T structure in there. So we have an abelian subcategory where we have then exact functors somehow hidden. If you work with this non-standard T structure, then again it fits into the correct theory. Yeah.
Sorry, question. So if we go back one step, so you call this A1, A2, and A1 plus A2, these are central characters, not weights of the GL pattern?
So in the decategorified picture, these are weights. And in the categorified picture, they correspond to these things here, which are the central characters. But you're totally right. Decategorified into weights. Yes. Yes. So decategorified, it's weights of the representation you categorify. Categorified, it's for me central character, but a central character you can again think in terms of highest weights, but unfortunately of something very different from the weight before. But you can think of highest weight. Yeah, it's exactly, I mean, a central character is like picking a point here. And there is a Verma module which has this highest weight. Yeah. So, and now back to these things which we had at the beginning. So there's this several pictures. So this was a decategorified picture. So we have your link is somehow cut in three pieces, a vector, and a braiding matrix. And then categorified in this world, the bottom would be a projective module. The middle would be a complex of functors, which you can apply to this projective module. And then the top is a projective module, and then the pairing is Howe. And because the projectives are projectives, they have no higher x. These functors are exact functors, so they preserve projectives. So this is just computing homs between complexes of projectives. So this is something pretty easy in principle. And so in case of Hovanov homology, we write these things down for the smooth version, so no crossings, but the smooth thing, explicitly in terms of explicit arc bimodules. And then everything here can be computed explicitly. It also can be computed via Hovanov-Lauda-Webster algebras, which have the advantage that they are much more general. So this is much better. The advantage of arc algebras is that you can see basis vectors on the nose and you see exactly how big it is. But it's a bit more cumbersome to calculate with it.
But the arc algebra somehow reduces the Hovanov original.
So the arc algebra gives. So I do a small extension of arc algebra, so where I allow not only cups but also rays. Then you can see when you vary over also these sort of rays like this. So then when you vary over all projectives, you categorify really the whole V tensor n. And if you would then restrict to V tensor n as a two invariants, you recover Hovanov on the nose. It's really on the nose.
But the income stuff comes in the middle of the braiding effect, not in the.
So this is what Hovanov. So for me, this braiding in the middle. So what I would do is I would take this braiding like this. I would smooth it like this. Then I close it in all possible ways at the top and at the bottom. Yeah, and then you have a differential there. So for me, this is a picture for a bimodule, and this is a picture for a bimodule. So and how it becomes a picture for a bimodule, I orient it in all possible ways, and each orientation gives a basis element of this bimodule here as well. So I have a concrete realization of this bimodule and this bimodule, and I have, in contrast to Hovanov, because I would close it in all possible ways at the top and at the bottom, I have an action here of this arc algebra A2, and here of the arc algebra A2, and here as well. Does it make any sense?
Complex C of the bimodule or
Oh yeah, I write sometimes functors and sometimes bimodules. So for me, the functors which appear here are given by tensoring with bimodules. So I switch back and forth.
say bimodule, you consider all possible orientation of the curve?
So I mean, talking about these arc algebras would take 2 hours, but at least. So let me just try to explain this bimodule. So this bimodule, I would say, I have to close this picture in all possible ways. And so closing means either like this, or this is also an allowed closure. So when I do it in all possible ways, at the bottom and at the top, is all. Yeah, this is, I think is all. So then I orient all of them. So for instance, this is an orientation. And this is an orientation, etc. So each of them is a basis vector of my bimodule. Then I give it a grading. I just count the number of clockwise arcs, clockwise cups or caps. This gives me the degree. So I get a graded vector space. And then I have to tell you how to act on this with the arc algebra from the bottom and from the top. And this is some sort of diagrammatical rule, which is somehow just rephrasing Hovanov's surgery procedure.
training on people here. For example, for this complex of bimodules.
Yes. Yes.
That's negative.
Exactly. Yes. So they, by now, this newest paper of Abu Zaid and Smith, I think they just reformulate our whole thing in terms of the Fukaya category. So I explained them somehow everything we understand, and then they rebuilt it. It took them, I think, 5 years. This is called extended arc algebra. So the difference between the arc algebra and the extended arc algebra is the extended arc algebra categorifies V tensor n, and the non-extended categorifies this piece, which is enough for not invariance, but it's totally unnatural for if you. I want to see the sort of whole category.
Once you know that complex is manifest, that one single complex that does the right then in terms of the cup, you know that you get confidence knowledge.
Yeah.
It's not that it's
Yeah.
matched, there's nothing.
Yeah. But you get a bit more, for instance. So for instance, what you can't see here is when I take, let's take two-dimensional representation, twofold tensor product. So this decomposes into the trivial plus the three-dimensional representation. Maybe I should write 3 now. So this thing is just a trivial one. So you don't see that one. But this one we want to see if we want to have colored Jones polynomial. So this is, from my point of view, the reason why Orbanov homology cannot produce good colored Jones polynomial. Because it just only sees this piece. There's no way you can get it. Because how one would usually do it, one would take this V3 and do some cabling procedure, and then you get coloring with this representation.
Isn't there some long story about people categorifying Jones Venn projectors?
Exactly. So you categorify a Jones Venn projection, and this is exactly projecting onto this V3 inside this V tensor 2.
I think
What this?
either a tremendous understanding of that procedure of the Jones Venn procedure.
I don't know. I have to ask Eugene. There is some. So I'm not.
Dealing with marginal spaces,
So okay, I can explain you why it's difficult, and then you can judge whether it's done or not. So to categorify this V tensor 2 in the middle weight space, I would use these categories or Purver sheaves on P1. And then you can take a quotient to Purver sheaves on one of the stratum. And there's one stratum which is a point, and then there's an open stratum. And one projection is nice, the thing is smooth, etc. But the other one is really bad. And to get this color thing, you have to project to the bad thing. And so I think geometers don't understand it. So I would say no. And you want to have something non-smooth because the point of this colored Jones polynomial is when you look at the formulas, how to get it, you divide by quantum 2 or something. And you want to make sense of dividing by quantum 2. And my interpretation of writing 1 divided by quantum 2 is, so let's say quantum 2, I normalize like this for the moment. So this is 1 minus q squared plus q to the 4 minus q to the 6, etc. And so this infinite sum indicates for you there's something which is not smooth. You want to work with infinite complexes to categorify this. And so geometrically, it's something non-smooth. The Jones polynomial, but when you go through the calculation, so the projection onto this space involves this. And there is a miracle that at the end, you get for the unknot quantum 2. But it's a miracle. This quantum 2, when you are honestly calculating Reshetikin-Turaev invariance, is something divided by something. And you should not cancel. It's not allowed to cancel because it has a meaning that you divide. And yeah. And people, of course, constructed some Color-Jones polynomial categorification where they did cancel. I mean, including Hovanov himself. But if you look at the categorification, it's not natural. It depends on many choices. And it's supposed to be not natural because it doesn't categorify the formulas which are in Reshetikin-Turaev. One should never, I think the main message is one should never jump. One should never look at the end result and categorify this. One should be able to do every step. And if you can't do every step, then something is wrong. Anyway, so this is then at the end result. And I think whatever kind of question you ask about quantum SL2, I think we can categorify it, I claim now. But yeah, it depends. So I can only say I think because I don't know which question you ask. But where are we now? So what we can categorify is, so I told you today a little bit about tensor product of exterior powers. And this is nicer than tensor products of arbitrary finite dimensional representations.
Can I say something about
Yeah.
that? Strictly speaking, that theory with two grades does not exist. It's just a formal construct. So they have not actually given a theory that categorifies.
Yes, I would
Because
agree.
it just doesn't exist.
Yes.
As you said, it's something you do at the very end.
Yes.
With
Yes.
some fun.
Yes, I agree. Yeah. So why is for us exterior powers, tensor products of exterior powers easier? So we use these category O's, and these category O's are extremely nice categories. They are highest weight categories, have finite global dimension, etc. So when I take tensor products of arbitrary representations, finite dimensional, I can realize them as quotient of tensor products of exterior powers. So in general, we will get quotients of these things, and we know exactly how to construct them. But many of them have not nice properties anymore. So often the category has infinite global dimension and things like this. But we know exactly how to construct them. But there is a reason why the exterior powers are better. And luckily, for the normal SLK not invariants, it's totally enough. So, and because otherwise we would not be able to compute much. So it's much better to take only the exterior powers. So we categorify this tensor product with intertwiners and UQ actions, but I never explained you how to take tensor products. So I only said, okay, take tensor product of exterior powers, and then you tell me which exterior powers, and then I take this parabolic and blah, blah, blah. But I can't do, here's a tensor product, here's another tensor product, and now I want to tensor them together. I can tell you what comes out at the end, but I can't do the procedure. And I believe that it's pretty complicated. And I mean, Ruki works on this since 10 years or something, and is still not, I think there's no paper so far. It definitely involves higher category structure, whatever you want to do. So the fact that this box diagram game works so well, it's what you can see there is it's based on standard basis vectors. And standard basis vectors tensor very nicely together. But the things, these cup diagrams, etc., which we use for the link invariants, these are not corresponding to the standard basis, and they don't tensor nicely together. So that's a good indication that things go wrong. But assuming that we can do like standard basis vectors, categorify them via Verma models, why can't we then do tensor products? The reason is we don't understand X between Verma models. And this is why I'm interested in computing X between Verma models, because I think if one understands this very well with the higher structure, which you guys maybe know from Fukaya categories, then one has a hope to categorify tensor products. So this is the motivation behind it. And the other thing, which I think is a big problem, is braidings. So we construct break-off actions, we construct not invariants, but we don't really categorify bratings in the sense we don't construct a braided monoidal 2 category, categorifying Reshetikhin into Raif's braided monoidal category. And the reason is braided monoidal 2 categories is something which is highly non-trivial. And so my second talk would be about, first of all, explaining why braidings, to categorify braidings is something not obvious, and hopefully convince you that we haven't done it yet, or at least it's not like in the literature easily, that it involves a good definition of braided monoidal category. And from what I see, it's either requires infinity categories on the nose, or it really means we have to rewrite many things which we have at the moment. But this
Grading sample part, I mean, sample part of the story that you've already told us that.
no, so what we categorified is an action of a braid group on a category. But an action of a braid group on a category is different from a braiding. And the difference is a braiding has to be natural.
I still want to understand natural.
No, it's not. So so let's not do it categorified. Let's just do it on normal categories. So if I have Reshetikhin to Raif theory, I can say on V tensor n, there is the action of the braid group VRn. So what does it mean? I have to give for every generator of the braid group, I have to give an endomorphism. And then I have to check that they satisfy the braided relations. That's it. So, but what is a braided monoidal category? A braided monoidal category is more than just an action of a braid group. The braid group action has to be natural. So, which means when I have morphisms between these V's, they have to slide through a braiding morphism. So if I have such a braiding morphism, and I have here a morphism, so this is let's say this is V tensor 2 and this is V tensor 2, and I want to braid them, and I have a morphism F from V tensor 2 to V tensor 2, and to afterwards this braiding, it's supposed to be the same thing as first do the braiding and then the F. And so this is not encoded by just saying I have an action of a braid group. It says nothing about this. So now imagine we categorify this. Then this thing becomes a complex of bimodus. This thing becomes Young-Baxter equation just tells you that the braid relation holds.
But
Okay. Okay. So no, you are right and half right, half not right. So what does the braid Young-Baxter equation say? Young-Baxter equation says this thing is equal to that thing. Okay? So now how can I read this? I can read this. I take this red crossing and I move it through this thing up. So now the blue thing I can think of a braiding, and this I can think as a morphism, and I move it through. So in situation where all morphisms are given by crossings, then it would be enough. But if you have here more morphisms than just crossings, you are in trouble. And if you do any of these categorifications, you would never expect that the only morphisms you have is braidings. So you have to be able to slide something through, something here through, which is very complicated. You don't even know how to draw a picture, except of such a picture. Yeah. Yes.
But in the no law that any other function other than braiding, because there's only one.
I mean, there are others. There's definitely other functors. Already, I mean, this braiding is smoothened from this and this. So what about this guy? So if I replace this red thing by this, what do you do? I mean, this guy I can do. and then build complexes out of these. The mess. So we are not far away from that, I claim. So, but yeah, this is what I want to explain next time, and somehow a partial solution to it.
So the issue arises if you want to get a full two categories, the one is.
Yeah.
Perfect.
Yeah.
Yeah, that's what.
And I mean, the issue arises already by trying to formulate what this actually means. A full two category, a braided monoidal two category. To write down a definition is non-trivial, or maybe doesn't exist in the way how we want to have it. I mean, people would say this is an E2 algebra in category in an E2 algebra in two categories. But the question is, what does this mean? Yeah. Yeah, so this is, I think, what I wanted to say. But
Very interesting to be want to write down a generator.
for what?
Description. You want to write down a generator's relation description. That's basically.
This is what I would like to have, but I tell you why it's